Pluto is a faraway, elusive, and prominent planet that was once considered part of our solar system. However, recent groundbreaking statements from well-known physicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into public discussion. They have proposed that this icy planet might be heading toward a potential collision course with Neptune. But how can such a scenario occur, and what would it entail? What would the consequences be of such a monumental event? Are we witnessing something unusual, an unpredictable phenomenon? Or is there something more to this impending cosmic disaster? Join us as we investigate the possible outcomes of a Pluto-Neptune collision. Pluto, which was once a planet but later reclassified as a dwarf planet, continues to be a subject of interest and investigation within the vast universe. Recent predictions by leading experts suggest that Pluto's orbit is alarmingly close to Neptune's, prompting astrophysicists Neil deGrasse Tyson and Michio Kaku to warn of the possibility of a disastrous meeting between these two celestial bodies, which could pose a significant risk to Earth. But how could Pluto be involved in such a collision? Pluto's orbit around the Sun is distinct from that of any other planet in our solar system. It takes an incredible 248 years to complete one full orbit. Since its discovery in 1930, Pluto hasn't even completed a single full revolution. However, the intrigue doesn't end there. Pluto's orbit is notable for its elliptical shape, which strays far from the nearly circular orbits of the major planets. What makes it even more unusual is its tilt. Pluto's orbit is inclined at an angle of 17 degrees to the plane of the solar system. Its path follows a far more erratic trajectory, contrasted with the more sequential orbits of the other planets, adding complexity to its orbital dynamics. Perhaps one of the most intriguing features of Pluto's orbit is where it comes into contact with Neptune's. For roughly 20 years during each orbit, Pluto actually travels closer to the Sun than Neptune does, defying the conventional expectations of their relative positions within the solar system. Naturally, this raises the question, why have Pluto and Neptune not collided? The answer lies in the gravitational forces that other planets exert. After Pluto's discovery, astronomers quickly set out to understand its strange orbital behavior. Contrary to the orbits of the other planets, which lie close to the solar plane, Pluto's orbit stands out due to its steep inclination and highly irregular shape. The puzzle deepened when it became evident that Pluto's orbit crosses Neptune's. Despite this, Pluto's orbit remains stable, demonstrating the intricate dynamics of celestial mechanics, specifically, the so-called three-body problem in space. Understanding how three objects like Pluto, Neptune, and the Sun interact gravitationally is key. This scenario is comparable to attempting to predict where these objects will be in the future based on how they started and how they influence one another. The stability of planetary orbits is ensured by a concept called non-concurrent libration. In the case of Pluto and Neptune, this means that whenever Pluto crosses Neptune's orbit, the two bodies are always positioned at least 90 degrees apart. This spatial separation prevents a collision between them. Another contributing factor is a term known as orbital precession, which refers to the slow vertical movement of a planet's orbit. Pluto's orbit indicates that when it comes closest to Neptune, or any giant planet, it is positioned well above their orbital plane. That adds another layer of defense against potential collisions. An additional factor in play is VSK wobbling, named after three researchers, Vladimir, Shapiro, and Kai, who studied how celestial bodies interact with each other's gravitational pull. This wobbling effect helps explain why Pluto's orbit, though seemingly chaotic, remains stable over long periods. The gravitational tugging between Pluto, Neptune, and the Sun influences Pluto's orbit in a way that keeps it relatively smooth despite its irregular shape. VSK wobbling demonstrates that even in environments of unpredictability, there are underlying patterns and forces that maintain equilibrium. Understanding this three-body problem is crucial to comprehending Pluto's relationship with Neptune and the behavior of distant objects in our solar system. Numerical simulations conducted in the late 1980s revealed that, despite stabilizing forces, Pluto's orbit is actually quite erratic. Small deviations in its initial conditions could lead to significant differences in its course over centuries. These simulations also showed that Pluto's orbit maintains stability over incredibly long time scales, hundreds of millions or even billions of years. To fully understand the dynamics between Pluto, Earth, and Neptune, it's essential to consider the gravitational influence of the giant outer planets like Jupiter and Neptune. The influence of Saturn and Neptune is significant because it controls the orbit of Pluto. Pluto and Neptune are in a special resonance. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This gravitational resonance helps keep Pluto's orbit stable. However, Neptune is not the sole participant in this intricate equation. Jupiter's massive gravity also plays a key role in stabilizing Pluto's path, while Saturn contributes to this dynamic as well. These forces working together ensure that Pluto remains on a steady course, possibly for millions of years, keeping it out of harm's way. Without these stabilizing forces, the solar system would be much more chaotic, with planets potentially colliding or being ejected from their orbits, triggering catastrophic consequences. The possibility of an upcoming Pluto-Neptune collision underscores the depth of celestial mechanics and the importance of studying the stability of orbits. By understanding these intricate dynamics, we gain a better comprehension of how the solar system functions and the behavior of distant objects. Despite appearances, Pluto's orbit is a testimony to the delicate balance of forces that keep it in place. Exploring space often leads to surprising discoveries, and Pluto's irregular orbit serves as a vivid example of the mysteries of the cosmos. The concept of orbital chaos illustrates how the orbit of a celestial body can be extremely sensitive to its starting conditions. In Pluto's case, even minor changes to its speed or position could significantly alter its long-term trajectory. Automated simulations have been invaluable in helping scientists study these behaviors. By modeling the ways Pluto and objects like Neptune influence one another through gravitational pull, simulations show how even the tiniest environmental changes can significantly impact Pluto's course. Though Pluto's orbit is stabilized by mechanisms like precession and libration, simulations have also revealed that it is far from consistent. Slight variations in its initial state can result in vastly different outcomes, making long-term predictions about its motion extremely challenging. Nevertheless, despite the apparent disorder, Pluto's orbit remains relatively stable over geological timescales, billions of years, suggesting that amid chaos, there is an underlying order to its motion. Predicting celestial movements, particularly for objects with irregular orbits like Pluto, is a massive challenge. The inherent unpredictability of these systems means long-term forecasts are full of uncertainty. Tyson's insights underscore a vital truth: even with centuries of astronomical study, our understanding of celestial mechanics is still evolving. Pluto's strange behavior challenges assumptions and forces scientists to confront the limitations of current models. What was once seen as a demotion, from planet to dwarf planet, has now become a spark for renewed curiosity. Meanwhile, Michio Kaku, known for his engaging explanations of complex scientific theories, echoes similar concerns. He warns that our solar system, while seemingly stable, is governed by forces we only partially understand. According to Kaku, Pluto's orbit may be a window into deeper gravitational resonances that affect the entire structure of planetary motion. Despite the mathematical elegance of orbital mechanics, the long-term stability of planetary bodies isn't guaranteed. A system as vast and interconnected as ours means that even a tiny gravitational nudge, perhaps from a passing object or a shift in another planet's orbit, could, over millennia, compound into something significant. Could this mean Pluto and Neptune might eventually drift into a more dangerous alignment? Some scientists believe such fears are overblown. The orbital resonance between Neptune and Pluto, specifically the 3:2 resonance, has protected the two from direct encounters for millions of years. Each time Pluto approaches the point where their paths intersect, Neptune is safely far away. It's a cosmic choreography that seems almost intentional. Yet, as advanced as simulations and theories have become, many elements, like external influences from objects in the Kuiper belt or passing rogue asteroids, still pose unknowns. The possibility that a distant gravitational force could slowly disrupt the delicate balance is not entirely outside the realm of scientific speculation. These uncertainties highlight the necessity for ongoing observation. Modern space telescopes, satellite missions, and deep space monitoring tools are helping researchers collect more accurate data. Instruments like the James Webb Space Telescope and probes like New Horizons, which visited Pluto in 2015, continue to reveal new details that reshape our understanding of distant celestial bodies. New Horizons, in particular, provided humanity with its first close-up view of Pluto, uncovering a surprisingly complex world with mountains of water ice, vast nitrogen plains, and possible subsurface oceans. These revelations transformed Pluto from a distant icy speck into a dynamic, geologically active dwarf planet. Its interaction with solar wind and its mysterious internal heat raise questions that extend far beyond orbit prediction. They speak to the very formation of our solar system. As more data accumulates, astronomers hope to refine long-term simulations and better understand the subtle gravitational interplays between all major celestial bodies. What seems stable today may not be stable forever, but with enough knowledge, we might detect early signs of instability long before they pose any real danger. In the end, the discussion of a Pluto-Neptune collision may be less about alarm and more about awe. It reminds us that even in what seems like cosmic stillness, everything is in motion. The vastness of space doesn't mean emptiness, it means dynamism, interaction, and endless possibilities. Pluto's story, with all its twists, discovery, classification, reclassification, and ongoing mystery, remains one of the most compelling in planetary science. It teaches us that science is not about final answers but about continuously refining our understanding of a universe that never stops surprising us. Reclassification as a loss, rather than an important modification, is based on our expanding understanding of space and Tyson's approach to celestial bodies. The mechanics of the heavens are one and the same. He sees discovery and evolution, orbital complexities like Pluto's, as indicative of how much more there is to learn about the universe. Despite Tyson's presence, he remains hopeful regarding the study of space. His views on Pluto's potential collision with Neptune suggest that numerous questions remain unanswered. Will Pluto collide with Neptune, or is this merely a momentary confusion in the ever-evolving cosmic system? Only additional time and study will provide the answers. At this time, we are left with even greater curiosity: how much is still unknown about our own solar system? The potential for a Pluto-Neptune collision invites further examination of the mysteries of the universe and challenges our understanding of planetary dynamics. The possibility of two heavenly bodies with drastically different properties colliding raises intriguing questions about how gravitational interactions shape the evolution of the solar system. A collision between Pluto and Neptune would not only have major implications for our understanding of orbital behavior, but it would also provide valuable insights into the evolution of the solar system itself. To understand the dynamics of a potential impact between Neptune and Pluto, it's essential to consider the characteristics of both planets. Pluto, though classified as a dwarf planet, contains a variety of elements and compounds in a frozen state, thanks to the icy outer solar system's extreme cold. Its surface is covered with nitrogen ice, and its atmosphere is primarily made up of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas giant, consists mainly of helium, hydrogen, and other lighter elements, with a deep, dense atmosphere. A collision between these two vastly different bodies would undoubtedly have a significant impact on both, potentially creating an event that could be seen from vast cosmic distances. However, it's important to note that Neptune's gravity is not the only stabilizing force in play. Jupiter, the largest planet in the solar system, also exerts a significant gravitational pull, contributing to Pluto's stable orbit and preventing it from venturing too close to Neptune's domain. Saturn's gravitational influence further complicates interactions in the outer solar system, making a devastating collision between Pluto and Neptune unlikely. While the gravitational pull of Neptune plays a dominant role in stabilizing Pluto's orbit, the complex relationships between other planets, like Saturn and Jupiter, further ensure that Pluto's path remains steady. However, research has also shown that the relationship between Pluto and Neptune is not as easy to navigate as it seems. A potential collision course is avoided thanks to the gravitational resonance between the two planets, where Pluto completes 2 orbits for every 3 Neptune completes. This creates a natural barrier that prevents them from colliding. This resonance, often described as a gravitational dance, ensures that while the orbits of Pluto and Neptune intersect, they never result in a collision. This mechanism is an extraordinary example of how celestial bodies can maintain a harmonious relationship despite the chaotic forces at work in space. Yet, the future of this delicate balance is not guaranteed. Small shifts in the positions or velocities of these planets could disrupt this resonance and lead to unpredictable consequences. These changes could be sparked by external forces, like the gravitational influence of an undiscovered planet or a passing star, or by internal events such as tidal forces causing gradual changes in the orbits of these bodies. Continued study and observation of Pluto, Neptune, and the surrounding bodies in the outer solar system are essential for understanding the long-term stability of their interactions. As new technologies emerge, scientists will be able to refine their models and improve our comprehension of the dynamics between these distant objects. New data may shed light on the delicate balance that keeps Pluto and Neptune from colliding, or it may uncover new forces that have the potential to alter their relationship in the future. As we continue to study the dynamics of Pluto and Neptune, a significant factor that has come to light is the possibility of an undiscovered object influencing their paths. This hypothetical object, referred to as Planet 9, is believed by some scientists to exist in the far reaches of the solar system. Its gravitational pull could alter the orbits of objects like Pluto, potentially pushing them toward new paths that might destabilize their current positions. While the existence of Planet 9 is still a subject of debate, its potential impact raises the stakes even higher. Because of the situation's complexity, in addition to the gravitational interactions between planets, it's important to think about the bigger picture, the context of how the solar system functions as a whole. The Sun, being the dominant gravitational force in the system, is gradually losing mass through the process of the solar wind. As the Sun loses mass, the orbits of all the planets, including Pluto and Neptune, could slowly expand over time. This process could shift their relative positions and influence their long-term orbital resonance stability. Furthermore, the outer solar system is not a fixed location. Comets and other small objects are always moving through it, causing their own gravitational forces to be applied. These passing objects could occasionally disrupt the orbits of distant planets, including Pluto, though such occurrences are uncommon and improbable. When combined, the impact of these diverse forces may ensure that Pluto's orbit continues to be dynamic, constantly adjusting in response to the gravitational dance that occurs between the planets. On a more speculative note, the possibility of a massive event, such as the collision of two smaller bodies in the distant reaches of the solar system, could also play a role in shifting the trajectories of objects like Pluto. If such an event were to occur, it might trigger a chain reaction that could have repercussions for Pluto's course. We cannot currently predict this, but it highlights the chaotic nature of celestial dynamics, where even minor events can lead to large-scale changes over time. Comprehending these scenarios necessitates sophisticated simulations and continuous observation. While we have a solid understanding of Pluto's orbital behavior, the true nature of its future course will be determined by a plethora of difficult-to-foresee factors. The ongoing study of Pluto, Neptune, and the outer solar system remains a crucial aspect of modern astrophysics, offering insights into the forces that govern our cosmic neighborhood. As our instruments grow more precise and our simulations more detailed, we are beginning to perceive the solar system not as a static clockwork of perfectly aligned bodies, but as a living, breathing system, one that evolves, responds, and shifts in response to both internal dynamics and external influences. The story of Pluto and Neptune serves as a compelling chapter in this greater narrative. Their interaction is a testament to the delicate balance and immense complexity that characterize celestial mechanics. Every orbit, every resonance, every gravitational nudge is part of a vast interplay that has been unfolding for billions of years, and continues to unfold right before our eyes. Yet, despite all we have learned, there remains a deep sense of mystery. We are still in the early stages of fully grasping the long-term evolution of these planetary relationships. The influence of hypothetical objects like Planet 9, the gradual dimming and loss of mass from the Sun, or the chaotic movement of trans-Neptunian objects, all contribute layers of uncertainty and wonder. In this cosmic dance, nothing is truly permanent. Over immense timescales, even the most stable orbits may drift. Resonances may break. Collisions once deemed impossible might become inevitable. These possibilities are not reasons for fear, but invitations to deepen our inquiry, to keep searching, observing, and questioning. Each new discovery, no matter how small, adds a new brushstroke to the portrait of our universe. It expands not only our scientific knowledge but also our philosophical perspective, reminding us that we are part of something vast, intricate, and beautifully uncertain. As we look further into the outer reaches of the solar system, and beyond, it becomes clear that the story of Pluto and Neptune is not just about two distant worlds. It is about the nature of change, the importance of balance, and the endless curiosity that drives us to explore the unknown. The cosmos is not a solved puzzle. It is a living mystery, and our place within it is still unfolding.